As we start topic 6 of chapter 3, rational functions, this is what a rational function looks like algebraically. That is, they're fractions, and they are somewhat complex as we look at them. Here, this would be linear because our x is only to the first power, while these, of course, are to higher powers. So this is the general form of a rational function. Now keep in mind the denominator could never be a zero. That is, the whole thing could never be a zero. That is undefined. So we're going to take a look at this. So in this first example, we see a linear rational function. That is, the x value is to the first degree. Now, we want to find what would make our denominator a zero. We could rewrite the denominator so that it was x plus 1, or we could have left it this way. We want to solve for x. So if we just transpose the positive 1 to the other side, we get a negative 1. So if x were a negative 1, it would make our denominator a 0, and that would make it undefined. So therefore the domain of this is that it could be all real numbers, but x could not be a negative 1. It would make our denominator 0. Now this also shows something else, that when we graph this, because that is what we have to do here, when we find the value that makes our denominator a negative 1, that is referred to, as we'll see shortly, the vertical asymptote. And they show us through some tables here, as they put various values in there for x, that as the function of x gets larger and larger, and we'll see that in a graph shortly, it never quite reaches a negative 1. So we say our negative 1 is called the vertical asymptote. And we'll see that in our graph down below. And plotting some of these points above, we end up with a graph that looks like this. Now notice if we use a dotted line for x equals a negative 1, that is this line right here, that is our vertical asymptote. Now also, if we note here, we get a horizontal line in which these graphs get closer and closer to the x-axis. So the x-axis here is our horizontal asymptote. And you might say, well, what if we have the equation of this line, a vertical line, as x equals negative 1, which in previous lessons we said that would be x equals a, is a vertical line, and if it's x equals negative 1, that's this vertical line that they're showing in a dotted fashion. What is the equation of this horizontal line, which is, in fact, the x-axis? Think about it for a moment. It's going to be some value of y. Y is going to equal what here? Which is the x-axis. What is the value of y right there? And if you said 0, that is correct. So our horizontal asymptote is the x-axis, or the equation of the x-axis is y equals 0. Now, in summary, let's read this. If a number c makes the denominator a 0, but the numerator a non-zero, in the expression defining a rational function, then the line x equals c. Now, we had often used the letter A for this in the past, is the vertical asymptote of the graph of the function, which we see right there still. Now, if the graph of a function approaches a horizontal line very closely, when x is very large or very small, we say that this line is the horizontal asymptote of the graph. And as we see it here, it's approaching the x-axis, and the formula for that, we said, is y equals 0. We said in example 1, the horizontal asymptote was the x-axis. But that's not always the case. As we look at this example 2 graph, we have this rational function. Find the vertical asymptote, and then later find the horizontal asymptote. Well, the vertical asymptote, we said, we're going to find by equating our denominator to 0. When we do that, we get 2x equals, transpose the positive 4 to the other side, makes it a negative 4. Divide both sides by 2. X will equal negative 2. So here our vertical asymptote is negative 2. But what is our horizontal asymptote? Now, the textbook goes through a rather elaborate procedure to build this, but the shortcut to it is, if this is your original item and you look at the coefficient of your variable, which is 3 here in the numerator, and is 2 here in the denominator, your horizontal asymptote will just be the ratio of these two numerical coefficients. So we'll say f of x here, which is in a sense a y, is going to be 3 over 2. So your horizontal axis is 3 over 2. And that's what they're showing right down here. So let's take a look at the graph now. So getting a number of points, you see now your vertical asymptote is a negative 2 right there. And your horizontal asymptote is 1.5, or 3 over 2. And again, the asymptote is defined as a line in which your graph approaches but never reaches. So this is what this looks like. Now we know how to find the vertical asymptote. We take our denominator and equate it to 0. But there is a little formula for finding the horizontal asymptote. And that formula, as we've seen, is we take the numerical coefficient as long as our variables are the same power, and it's just that ratio, 3/2. Now in example 1, there wasn't an x value, but in a sense, there could have been a 0x, which has no value, but it would have been a 0/1, which is this one here. And 0/1 is 0, which we said was the horizontal asymptote for example 1. So a good little rule, you want to be sure to include this in your notes. And in a sense, you can think of it in this formal way, AX over CX. So it's the ratio of A over C would be the horizontal asymptote. Now, as we look at other rational functions, they may have a degree greater than 1, so these functions can be more complicated than those in examples 1 and 2. The graph may have several vertical asymptotes, as well as peaks and valleys that we mentioned earlier. All right, so they want us now to graph this particular rational function. Let's see what we know about it here. Well, we know we can find the vertical asymptote by equating our denominator to 0. And that's what they're showing here. So this is the difference of perfect squares that factor into its conjugates. When we take each of the conjugates and equal it to 0, we get a -2 and a 2. So these will be our vertical asymptotes. Now when we go to find our horizontal asymptote, again we look here and we see we have x to the second, x to the second. Here there's a 2, there's a 1, and if we use that formula, f of x c over a, where this is our c and this is our a, then we get 2/1, which will become a 2. So our horizontal asymptote will be a 2. So we found out a number of things about our graph. So they're showing us some other stuff here. I don't know if you can see the 2 here. So after getting some points here, let's take a look at our vertical asymptotes at -2 and a +2. And then our horizontal asymptote, which we said was 2. And then our graphs sort of like this. But we also get a point here. And again, it's a matter of getting some data and filling it into the equation and getting some points. Now the textbook gives a very good video as well, and I'm showing part of it here. Let's take a look at it here.
Graph f of x equals 3x squared divided by x squared minus 4. So step 1 is to determine symmetry. So if I take f of the opposite of x And now substitute the opposite of x here and here. I would have 3 times the opposite of x squared divided by the opposite of x squared minus 4. And so the opposite of x quantity squared is x squared. So I have 3x squared divided by the opposite of x quantity squared, we just said, is x squared. So the denominator is x squared minus 4, which means it's exactly equal to f of x. And then that tells us that the graph is symmetric with respect to the y-axis.
So he's giving some good information here about symmetry. And let's continue.
Now, step 2 is to find the y-intercept. And remember, that means we evaluate f of 0. That means substituting 0 in place of x here and here. So we would have 3 times 0 squared divided by 0 squared minus 4. In the numerator, 0 squared is 0 times 3 is 0. In the denominator, 0 squared is 0 minus 4 gives a result of negative 4. But now 0 divided by negative 4 is equal to 0. And so the y-intercept is 0. So the graph passes through the origin.
Okay, so that is a good point, something we've used before when we want to find the y-intercept. When y is 0, our value for x will be 0.
3 is to find the x-intercepts. So step 3, find x-intercepts, and we do that by setting the numerator equal to 0. The numerator is 3x squared equals 0. And so, of course, solving this, x will be equal to 0. So the x-intercept is 0, which verifies the fact that the graph passes through the origin.
So our ordered pair then of intersection is 0, 0, which is the origin.
Step 4 is to find the vertical asymptotes. So step 4, and that means that we set the denominator equal to 0. So x squared minus 4 is equal to 0. We saw.
And we did this one.
All for x. We add 4 to each side. X squared equals 4. And now we take plus or minus the square root of each side, so we get x equals plus or minus 2. So the vertical asymptotes occur when x is equal to negative 2 and when x is equal to 2. Step 5 is to find the horizontal asymptote, in which case we need to look at the degree of the numerator and the degree of the denominator. The numerator has degree 2, the denominator has degree 2, which means they have the same degree, and therefore we look at the leading coefficients, 3 and 1, and we use that to determine the equation of the horizontal asymptote. So step 5, the horizontal asymptote is y equals 3 divided by 1. That is, y equals 3 is our horizontal asymptote. Step 6 is to find or locate points that are between and beyond the x-intercept and vertical asymptote or asymptotes. With the x-intercept being at 0 and the vertical asymptotes at x equals negative 2 and x equals positive 2, we want to evaluate the function at the following points. I'll make a table. Negative 3 would be beyond x equals negative 2. So let me make a table. I select values of x, and we evaluate f of.
And remember, this is our typical t-chart, where this is the x and the f of x is y.
X. as I said, we start with -3. And when I substitute in -3 in place of x here and there, and then evaluate it, the result is 27/5. Now we'll select -1 because that's between the vertical asymptote of x equals -2 and the x-intercept of 0. When I substitute in -1 for x here and here, my result is -1. Let's now substitute in +1. And when I substitute in +1 here and here, the result is -1. Then I'm going to substitute in +3 for x here and here, and my result is 27/5.
So you're starting to see some of the symmetry that we spoke about, and you're getting a couple of points. And again, our textbook's not showing this, but this is what and how it's done.
And then one more point, let's substitute in 4. And when I substitute in 4 here and here, the result will be 4. So the next step is to plot these points, which I've done on the next illustration. So let's take a look. So I've plotted each of the points. You can see 2 of the points here, 2 more of them over here, and then a 5th point there. Now what we'd want to do is connect the points within each region, that is between the 2 vertical asymptotes, with a smooth curve.
And I particularly like this part because it's showing, you know, the technique of the author who's had a lot of experience doing this.
And we want to connect these points that are in this region, separated off by the horizontal and vertical asymptote. And then over here, draw, because we talked about the symmetry being across the y-axis, we know that whatever we draw here, we're also going to draw here. So now let's take a look at that final graph. And we can see now we have this curve and this curve symmetric about the y-axis. And of course, drawing this part, we also see it is symmetric across the y-axis. So it does help to see the graph, and you can now see that the y-axis symmetry is obvious. Graph.
So a nice job. As a little review of this, notice his was slightly different, but something very similar. As we continue going over the textual material, applications. Rational functions have a variety of applications, some of which are explored next. For instance, in natural science, if you have a pollutant that is in some situation, whether it be water or air, you can take the pollutant out, and of course that costs money. Now, we have a situation in which, as you can take out a little bit, and that wouldn't cost very much, and you can take out a little medium amount, and that would cost a little bit more. But then when you get toward the very, very end, to try to get that last little bit out, it could be quite expensive. And we think of this then in a cost-benefit function. And they're suggesting that this function would relate to the cost of removing X% of a certain pollutant. And what would the domain be? Well, it would be in the first quadrant, and it would go in a sense from 0 to 100, which would be 0% to 100% that can be removed. So what would be the cost then of removing 100%? Well, we would put 100 where the X is here, and that's of course what they've done. And that would equal 300, which is actually, since this graph is to the thousands, $300,000. Wow. Now, as we look at the actual curve and data that was placed in there, we can see if we want to remove 90%, which would be down here, we'd go up to this point, and if we went over, it would be about 101,000, and then 95%, which would be about there, that would be 155,000, which is what they're describing there, and so on and so forth. So to get 100% of it removed would be 300,000 at 100%. Okay, so they're not asking us to actually draw these, but to be able to interpret the result if this is the rational function, and then what would be the cost of removing that pollutant. Okay, let's go on. Another item that they have related to rational functions is the product exchange function. This gives the relationship between quantities of two items that can be produced at the same machine or factory. For example, an oil refinery can produce gasoline and heating oil, or a combination of the two. A winery can produce red wine, white wine, or a combination of the two. So the next one illustrates this, in which you have a product exchange function for fruit of the earth winery, for red wine X and white wine Y. And they figured out this function can be expressed this way. Now again, if you graph this, what would be your parameters for your graph? Well, you can only have values greater than 0, so we'd use the first quadrant. And if you let x equals 0, put it in there, you get y is 125. And if you let y be 0, we get x equals 2000. We actually see this on the next page. So we see this will go up to about 125, and this goes down to about 2000. So, for instance, if you wanted 800 cases of red wine, how many white wine could you produce? So you go up here, and then you go over, and it looks like about 45. So you can pick out various things by looking at your graph. Now in our last example, we're looking at a business, a retailer who buys this many specialty light bulbs from a distributor each year. But in addition to the cost of each bulb, there is a fee that he has to pay to place an order. So he wants to order as few times as possible. And also there is a storage costs that are higher when there are fewer orders. So he wants to have, that. So it gets to be tricky as all of these things interrelate. But past experience has shown that they could use this cost function here. And if you were to put that into your calculator and you set your window to the max of 2500, again, you wouldn't have any or 0, you would have none, no. So it's somewhere between X and the max that you need. So taking your tracing function on your graphing calculator, and again, we don't do this, you kind of bring it down to this low point. So that's the minimum then of your graph. So for your X value, that's about 150. And for your Y value, that's about a value of $1,494 if we round it off, and there's what they're showing here. This leads us to our exercises, and you'll be doing some of your study plan. But let's just look at some of these. Now, what would be your vertical asymptote here? Remember, equate this to 0. That's going to be a -5. And what will be your horizontal asymptote? Remember, it's 0x, so 0 over 1 would be 0. That would be your horizontal asymptote, which is the x-axis, or y equals 0. And basically, this is what you're going to be doing, and good luck to you.